Hello, my name is Pat. I and my colleague present a paper toward Growable robot, exploring and integrating flexible biological matter with electronics. The direction of recent research suggests the convergence of digital and biological systems, where researchers design and engineer technology that share many aspects of living organisms. In this paper, we explore a step toward Growable robotics, a type of robotic system that has the ability to self-grow either a part of or its whole body into a functional shape with minimal help from the external system. In the conventional context, the fields of robotics entangle with the design, creation, process, and the use of robots, as well as electrical systems for control, sensing, and data processing. However, as technology becomes ubiquitous and pervasive, the scope of the research has expanded to the new domain of applications, including social robotics, robots for education, personal robots, and exploration robots. To tackle the emerging utilization, the field of robotics has been radically transformed through the advancement of material science and engineering. Researchers have experimented with a wide spectrum of alternative materials for robot body. For example, a researcher used inflatable and soft material to create a skin of a robot that is flexible. Researchers also look at the living organism, taking inspiration from biological systems, to design robots that mimic forms and functionalities of animal and plant. The example in nature of functional structure made of soft and flexible materials, from muscular hydrostats such as elephant trunks to octopus tentacle that can bend and extend and twist. Beyond that, researchers have also looked into digital augmented biological systems that combine living matter with electronics. The researcher present a 3D printed fluidic device and wearable technology designed to culture microbial communities using a bio-inspired algorithm for additive manufacturing of the device. Researchers also developed growing living actuators made from printing bacteria Bacillus subtilis natto on a fabric that can synthesize responsive bioskin. This composite can react to body heat and sweat, causing the material around the heat zone to open, enabling the sweat to evaporate and cool down. As the boundary between digital and biological is blurring, and the bio-inspired engineering has converged with the biological augmented engineering, the futurists envision the future of robots that fully assemble an organism, having a growing tissue and the body with the ability to self-heal. Even though the technological advancement of today cannot reach the vision, some researchers have started looking into self-grown flexible materials, such as microbial cellulose, for biological augmented wearable technology. These microbial cellulose can be produced by various species of microbes, such as Acetobacter, a agrobacterium. The formation of cellulose occurs on the upper surface of the supernatant film. Cellulose production was reported to be stimulated by the addition of lactic acid, methionine, tea infusion, and corn steep liquor. Microbial cellulose has various applications, from industrial foods, cosmetics, nonwoven fabrics, and others. Researchers and companies have also explored the use of cellulose film for medical purposes, such as a temporary substitute for human skin in the case of burns, surgery, and dental implants. Further, researchers have used microbial cellulose as smart materials, such as an electronic biopolymer actuator for biomedical applications, cellulose-based conductive composite, and electronic paper display made from microbial cellulose. Our work expands the scope of soft and flexible robotics by proposing the use of self-grown microbial cellulose as the body of robots that enclose the electronic circuits. We developed the proof of concept prototypes, analyzed the potential application based on the properties of the material, and suggest the future direction in the growable and biological augmented robotics. Methodology. The idea of growable robot is defined as a type of robotic system that has the ability to self-grow either a part of or its whole body into a functional shape, with the minimal help from the external system. We demonstrate the process of creating the growable robot using microbial cellulose by prototyping a simple rover inspired by NASA's folded origami robot. The process consists of three major parts: microbial cultivation, robotic design, and electronic implant. The production of microbial cellulose is derived by the synthesis of cellulose by kombucha fermentation, a process within the symbiosis between yeast and acetic acid bacteria. The cellulose synthase is considered to be the most important enzyme in this process. The metabolism inside the microbes convert monomer of sugar into a polymer with the enzyme catalyst and cell assembly process as part of the cell growth. To start cultivation, a growth medium for the microbe was prepared using black tea, water, and sugar. The starter culture, known as SCOBY, are mixed with the proportion of 4 tea bags, 1 liter water, and 100 ml of kombucha solution in room temperature. The compact cellulose network structure with assembly of the ultrafine microfibrils formation will happen at the surface level of the solution within 5 to 15 days. The cellulose would conform to the shape of the electronic component as well as the container. Robot design. To demonstrate the possibility of a growable robot based on the microbial cellulose, we developed a simple robot with 2 wheels. The shape of cellulose produced in the process is flat and conforms to the container of the microbe. Therefore, we designed a process for the sheet of cellulose and electronic device to fall into a functional shape. We deploy a square-shaped liquid container with the size of 50 cm by 30 cm to start the process. The level of thickness of cellulose sheet can be manipulated based on the temperature, ventilation for oxygen supply, carbon source or sugar, and pH value in kombucha solution. Electronic implant. The robot consists of 1 main control circuit, 2 driving servo motors, energy storage, 1 solar cell, 2 LED, and a radio communication circuit. The electronic components are protected by the insulator and placed in the microbe container in the area that was designated. As the microbe grows, the cellulose would conform to the shape of electronic component as well as the container. After 14 days of cultivation, the cellulose sheet with the electronic part are folded and removed from the container for the material to dry. The microbial solution in container will remain active for the next cycle of cellulose synthesis and robot creation. Result. By sampling the microbial population in the starter culture, we found that the concentration of yeast and bacteria are 2.1 times 10 to the power of 6 CFU per milliliters and 1.2 times 10 to the power of 7 CFU per milliliters. The microbial cellulose grown in the chamber once dry was able to support electronic circuits as the exoskeletal body while maintaining the flexibility of the material. Beyond developing the prototype of a growable robot, we explored the material properties of the microbial cellulose that are essential for robotics, renewable, self-healing, and shape-changing. Our preliminary findings show that the microbial cellulose is highly regenerative and flexible. After the cellulose sheet is taken out, the continuous cellulose formation cycle happens with the same duration. These results demonstrate a promising sustainable process of using cellulose for the future robotics design and mass manufacturing. We experiment with the process of self-healing and shape-changing qualities by creating an open hole on the material and putting the growable cellulose back to the microbial container. We found that within 5 to 15 days, the material regrown to heal the open wound and conform into the new shape. These properties suggest the future investigation on the use of self-healing and shape-changing properties for designing generative robots with the capability to perform and adapt to the extreme scenarios. Limitation and possibilities. Our preliminary experiment also point out limitation of the material, which open up the possibilities for the future in-depth investigations. First, the process for the microbe to produce the sheet of cellulose is in the order of a week. The trade-off between time and self-growing capability is the design constraint that must be considered of the design process. However, for the use case such as interplanetary exploration, where the duration of the mission is long and the time factor is less of a concern compared to the ability for the robot to heal itself, this type of material is highly valid. Second, in the current prototype of the robot, the process of folding requires external force on the self-grown material in order for it to achieve the functional configuration. However, in the future, it is possible to implant the shape-changing alloy inside the cellulose for the material to self-assemble into the functional shape upon application of electricity. Third, the strength of cellulose in the prototype requires an improvement in order for the robot to efficiently carry on a full-fledged mission. There is a need for the future study to investigate deeply into the factors that contribute to the pathway of the cellulose production. Also, the development of composite material based on cellular structure is one possibility to improve the material quality. Future research. As the possibility of self-grown robotics is limitless, we propose three directions for the future research and investigations. First, the researcher could experiment with the properties of self-grown material and pushing the physical limitation discussed in the prior section. This requires in-depth knowledge in the biochemical process of this microbe, as well as the material science in order to develop a physical material with the biological behaviors. Second, the researcher could explore the integration of microbial solution inside the robot, so the process of cell healing and self-growing can simultaneously happen in the real time, without having to separate the robot from the growing environment. To achieve this feature, the researcher could mimic the human skin structure and develop a synthesized material with an artificial blood vessel for the microbe to grow and produce cellulose in the real time, while getting nutrients. Finally, the researcher could explore the novel application of global robotics, which could potentially include wearable robotics, space exploration probes, and a humanoid robot that has the ability to regrow skin like human. In conclusion, our work shed light in the new area of soft and flexible robotics by proposing the use of self-grown microbial cellulose as the body of the robot and electronic circuit. We developed a prototype, analyzed the possibility and limitation of this application, and suggest the future direction in the growable and biological augmented robotics.